I'm from Bulgaria, but I was recruited from South Africa because I was doing my postdoc at that time over there. And so I've been working in Riga since 2012, and now at the Laser Center, and now in the last year I became a researcher here at the Institute of Atomic Physics and Spectroscopy. So as you can see, we have a lot of collaborators from Russia, St. Petersburg and Novosibirsk, and now since Igor is gone, also from Kingdom of Saudi Arabia, where also one of our bachelor students left for. So we study interactions of light and matter in atomic or molecular systems. What happens when you have a two-level excitation scheme and a laser coupling the two levels, which is the Bayer state picture. The laser splits those two levels in two, and it creates the so-called drift states, which are linear combinations of final and excited states. And the distance between them is combination of the radio frequency and the tuning of the laser. And the radio frequency characterizes the interaction between the atomic transition, which is the dipole moment, and the electric field of the laser. What's the situation when you have more complicated scheme? Say you have a two-level scheme which already has the strong coupling with the laser and creates drift states, and then you probe it with a weak laser from the ground state, so you can observe the population. What happens is the fluorescent signal gives you a two-peak structure, which corresponds to those drift states, the fluorescence from the drift states. And if the laser is on resonance, then this structure is symmetric. If it's not on resonance, then it's anti-resonant. Of course, atoms and molecules are more complicated than just two-level systems. You have a lot of fine and hyperfine structure components. And in realistic systems, if you want to do an experiment, you have to take care of this. So for each atom and molecule, you have different constants that do the splitting between the fine and hyperfine components. In a multi-level system like that, instead of just two drift states, you have multiple drift states. And actually, according to Morris and Shore, in a paper from 1983, they show that not all of those drift states are actually visible. So some of them are bright states and some of them are dark states, and they show exactly what's the number of bright and dark states in a multi-level system. The bright states are the ones that are coupled by the interaction, and you can see fluorescence from them. The dark states are not coupled, so you cannot see them by observing the fluorescence. And the number of dark states is the minimum between the difference between the number of excited and final levels, and the number of bright states is the minimum between those two numbers. So we took a realistic system in sodium, and with ground states 3s1/2, intermediate state 3p1/2, and final state 5s1/2. And we also studied different combinations of those states and different J and F levels. And we wanted to make a model that describes the systems and see how the fluorescence from this level is going to look like. And of course, in that model, we had to include the hyperfine energy shifts that I talked to you about before in previous slides, and also the transition dipole moment, which depends on the fine and hyperfine structure moments and numbers, and also on the time. So all of this was incorporated in our model. We used two models. One of them was a simple Schrodinger's equation, where you just take the wave function and you decompose it in coefficients with some probability amplitudes, and then you solve the Schrodinger's equation for those probability amplitudes, and you find the fluorescence for the upper state. We also include the interaction with the lasers, of course, with the rapid frequencies, and some lifetimes for the natural decay rates of final and intermediate state. And the second model that was developed by Nicola Vysogolev and Kaspar Schnitzerlis is called the split propagation technique. There you can also decompose your wave function in different coefficients, and then you form the density matrix elements, and to find each density matrix you have to apply the evolution operator to the density matrix, and the evolution operator consists of different parts of the Hamiltonian. So they divide the Hamiltonian by three parts: the first laser, the second laser, and the decay rates that we have in the system. And after that we compared those two models. So for the excitation scheme, there is 1/2 3p, 1/2 5s 1/2. We got the following results. So first, when the coupling field is weak, you see just peaks that correspond to 2-photon excitation. Then as you increase the rapid frequency of the coupling field, you observe the creation of the dry states. And in this case, according to the Moirish-Shaw transformation, you should have no dark states, just bright states. So indeed, as you increase your rapid frequency to a big number, you see that all the peaks are fluorescing. So these are only bright peaks. And then we saw another case. We worked in another case. There is 1/2 3p, 1/2 and 43/2. In this case, according to the Moirish-Shaw transformation, you should actually have some dark states. And indeed, when we calculated the dry states energy versus the rapid frequency, you see that some of those states are affected by the laser field, so the energy changes. But some of those states are not affected, so these are the dark states, which the energy stays the same all the time. And these states, the dark states, you cannot really see because they are dark and the fluorescence is 0. And the bright states just they keep shifting the rapid frequency according to this picture. And here is a comparison between our two models. For a small rapid frequency and for a big rapid frequency, the split propagation technique and the Schrodinger's equation, and you see that we can get good agreement between those two models, so we are more confident in our results. And then we looked at another excitation scheme. There is 1/2 3p, 3/2, 3d 3/2. And we saw some quite unexpected results. As you increase the rapid frequency, you see appearance of some peaks, and then you see disappearance of some other peaks. And at first we thought that those peaks that disappear are dark states because they don't fluoresce. But in reality, it turns out that they are bright states because their energies actually shift with the rapid frequency. And another similar results were obtained when you have the 3D typecast for final excitation level. In that case, also you have disappearance of some peaks which turn out to be bright ones, but in this case they are the ones on the inner side of the spectrum, while in the previous case they were the ones on the outside of the spectrum. So how do we explain these results? Our Russian colleagues calculated the gray states in the 3p 3-half 4d 3-half coupling scheme, and again you see that for some cases, for some Zeeman sublevels you have dark state operation, and for some other Zeeman sublevels you have the creation of bright states. And these are the bright states that some of them actually disappear when you have the increase of radio frequency. Here is the coupling scheme between all the between all the hard-to-find sublevels in the system. And from that you can actually see how the excitation goes and which state gets excited and which state does not get excited. So here are the results for this excitation scheme 3s 1/2, 3p 1/2, 4d 5/2. So in black you have the excitation from the ground state f equals 2, and in brown that you have the excitation from the ground state f equals 1. You see two interesting parts. The first part is that indeed first you have the appearance of the bright states, but then they disappear, as in the previous cases that I showed you. And the second interesting case is that the situation is that the excitation from f equals 2 and the excitation from f equals 1 ground state, they're completely independent, so they don't really overlap, which opens in the future some possibilities to actually excite selectively from each ground state at wish. And so in conclusion, we studied the formation of bright and dark states in sodium using two different methods, the Schrödinger equation and the split propagation technique, and they gave similar results. In one of the cases, we see just creation of bright states but no dark states. In another one, we see creation of bright and dark states according to the moisture transformation. In this case, we see bright peaks that disappear, and they're the ones on the outer side of the spectrum. In this case, we see bright peaks that disappear, and they're on the inner side of the spectrum. And in this final case, again we see disappearance of the bright states. And also we see what is interesting, that excitation from the different ground state components, F1 and F2, are independent of each other. And in the future we want to study the possibility to use this excitation scheme for two-component large amplifications. And this was funded by the Fotonika project, also a volume exchange, staff exchange program Kulima, and the one Lithuania project from the last 4 years. And thank you for